Lesson 2-7, Derivatives and Rates of Change. Objective. What is a derivative of a point graphically, numerically, and algebraically? All right, so we're going to take the secant line. A secant line is a line that intersects a curve in the neighborhood of two places. We're going to take a look at its slope, which is right here. And what we're going to do is we're going to have x approach A. So we have the specific point and we have the general point. We're writing the slope, which is called a difference quotient. We're allowing x to get closer to A, and when we do that, the secant becomes more and more like a tangent. This is the page I'm referencing. This is a GeoGebra activity here, and what I'm going to do is I'm going to show you how a secant becomes a tangent. All right, so here's our specific point A, f of A, and here's our polynomial. And the slider is going to force this point, as h goes to 0, it's going to force this point closer to this point. So I'm going to move it a little bit, and you can see that h is 0.8, it's 0.3, it's 0.28, and then you can see the h is getting closer and closer, and the secant is looking more like a tangent. And once it hits the point, it disappears because it's undefined. But if I move it across over just a little bit so that there is some h, you can see that tangent. And if you want to play around with this, go to the site right here, and you can take a look at other places on the curve, and again play around with the h so that you can see these tangents. All right, so the definition of a derivative at a point is to take a look at the difference quotient, and in this case it's using the h idea, and we're letting h go to 0. Letting h go to 0 forces this point closer to this point. Now the alternative definition is to work with a specific point and a general point and make x get closer and closer to A, and this forces the secant to get closer and the secant line to look more and more like a tangent line. All right, here's an example where we start from scratch. You might want to draw yourself a picture just to see what's going on here. This is our parabola, and at point 1, 1, what we're looking for is the equation of this tangent line, the one that you saw in the exploration. We want to find it analytically. All right, we know that an equation of a line requires two things. One, it requires a slope, which in this case will be f prime of 1, and 2, it requires a point, which we know is at 1, 1. So what we want to do is find the slope right here at 1. All right, if we go to the first definition, we're going to take a look at f prime of 1 is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And now I'm going to substitute those input values into h. So this is going to be 1 plus h quantity squared minus 1 quantity squared all over h. Limit as h approaches 0. This is going to be 1 plus 2h plus h squared minus 1 over h. The ones are going to cancel, and now I can divide both parts, h's into both parts, so I'll have the limit as h approaches 0 of 2 plus h, and that limit will be equal to 2. So this tells me that this slope is 2. And now I can write the equation of the line in point-slope form. Y minus 1 is equal to 2 times x minus 1. And that will be the equation of the line. You can leave it this way on a test. If you don't like it this way and you have to get into mx plus b form, then you can go through the extra steps. But I do want to remind you that if you make a mistake simplifying, then it will cost you. Now, the other way to do this problem was to find f prime of 1. We could have taken the limit as x approaches 1, and we could have substituted x in here, that's x squared, then substituted 1 in here, 1 squared, all over the difference of the input values, x minus 1. So this is going to be equal to the limit as x approaches 1, and then this will be, if I factor, x plus 1, x minus 1, all over x minus 1, do a little reducing, evaluate the limit, and that's going to be 2. And 2 is what we got from this previous exercise 2. So it's using both definitions to show you how you can get the slope, the instantaneous rate of change. All right, well, so what is the purpose of finding the equation of a tangent line? And the purpose is that this tangent line is going to really tell us what's going on locally. And because if you go ahead and you zoom in, you can see that the tangent line and the curve pretty much model each other. As long as we're close to that point of tangency, that tangent line models what's happening in the graph. Okay, I'd like you to try this problem. Go ahead and find the equation of the tangent line to this hyperbola, and stop the screencast, and then resume, and I'll go ahead and talk you through it. Okay, so let's go ahead and go through it. If you had difficulty, then you can watch as I go ahead and do the problem. We want to find the equation of the tangent line. Equation of the tangent line requires two things. One, it requires a slope, and that slope will be f prime of 3. And 2, it requires a point, and that point is 3, 1. So our work is to figure out the equation at 3. So I'm going to take the limit, and I'm going to use the first form. H goes to 0, and I'm going to do f of 3 plus h minus f of 3 all over h, and this is equal to f prime of 3. And then I'm going to put 3 plus h into the equation, so this is the limit as h approaches 0 of 3 over 3 plus h minus 3 over 3 all over h. So this is the limit as h approaches 0 of 3 over 3 plus h minus 1 all over h. Now I'm going to get a common denominator, so I'm going to multiply by 3 plus h over 3 plus h right here. And then I'm going to, let's see, how about if I move up here? So I get the limit as h approaches 0 of 3, take away the quantity 3 plus h all over 3 plus h all over h. And then that becomes a limit as h approaches 0 of, and this is going to be negative h, and then remember that I can multiply numerator and denominator by 1 over h, so there's a little reducing, and then these two become my denominator, so this is going to be h times 3 plus h. Okay, I can do a little reducing, and now I'm going to get the limit as h approaches 0 of negative 1 all over 3 plus h. I'm going to let h go to 0, and so this answer will be negative 1/3. Okay, so now I know that the slope is negative 1/3. And now I'm able to write the equation of my line. Y minus 1 is equal to negative 1/3 times x minus 3. And you can see by the picture that it is a negative slope, which I have right here, and I have my point. Okay, so in general, when we have a position function, when we take the average velocity, it's a slope, And if we allow the h to go to 0, we have instantaneous rate of change at a particular point, and that will be known as instantaneous velocity. Okay, suppose that a ball is dropped from the upper observation deck 450 meters above the ground. What is the velocity of the ball after 5 seconds? Okay, one of the things that we need to utilize is we need to be able to find the position function of a free fall object, which is S, which is equal to f of t, so it's depending on time, is equal to 4.9 t squared, and that utilizes gravity. Okay, so the velocity will be equal to the limit as h approaches 0 of f of, and we're doing it at 5 seconds, 5, and what we're going to do, yes, instead of using 5, we're going to use an A, where A stands for, in this case it'll be 5, but we want to use a more general equation, plus h minus f of A all over h. And what we're going to do is we're going to take the limit as h approaches 0, and I'm going to put a plus h in the formula, squared, minus, and then I'm going to put a in the formula, a squared, all over h. And I'm going to go through the process of finding the velocity, and this will be the velocity at a. Now on this next slide, all of the work is done, and you can see it's being expanded, and then there's some cancellation, and then there's some reducing. And what we get here is we get a formula. We can substitute any point in here, and in our case we're going to want to substitute the number 5. And when we substitute the number 5, we're going to find the velocity. Now, the biggest advantage for using A instead of 5 is to be able to answer part B. How fast is the ball traveling when it hits the ground? So right now we have this building, and it is free fall, and what we want to know is we want to know what the velocity when it hits the ground. And we have a nice velocity formula, but the velocity formula needs a time. So when it hits the ground, we really don't know the time. If we knew the time, then we could find the velocity, and that's the problem here. So let's take a look at how we can go about finding that time. And finding that time requires that we go back to our formula, S equals f of t equals 4.9 t squared, and we're going to put 450 right here in our S, and we're going to solve for t. And when we do that, we get about 9.6 seconds. So that's when the impact it hits the ground. We're going to go back to our velocity formula that we derived, and it was 9.8a, and for a we're going to put the 9.6, or be more accurate and put the square root so we can get the highest degree of accuracy. And so this is the velocity that we're going to get when it impacts the ground. And this is the end of 2.7 notes, part 1.